Okay, I believe we are live. I believe we're live. Let me just make sure that everything is working, that audio is working. Hold on. Um, yeah, okay. It seems like everything is working. Awesome. So welcome back, everybody. I know it's been a long time, but I've been very busy, and I did not have time to continue this series of reviewing my physics lectures. But midterms are over. I didn't do too well on the physics midterm, but I didn't get the grade back yet, so I hope I did well. But now that we're starting a new thing, at least to me, I'm going to start this up again, and I hope that I'll be able to stick with it. So stick with me if you want. There's a massive gap of knowledge between the last videos and this video. I hope that I'll be able to explain things. Yeah, let's just hope that it works out. This is my screen where I'll be writing. I'm going to hide my camera for most of this so that you can see the whole screen and so that things are a little bit better. Yeah, that looks like it's okay. And yeah, let me just give a brief overview of what we're talking about today. So we're going to be talking about momentum. Momentum, which is awesome because last semester we did Newton's laws and all this jazz, but we're going to be talking about momentum in a quite deep level. That's what the last lecture was on. That's what I'll be talking about today. I'm going to give a brief overview of what momentum is, how we understand it, and then basically we're just going to be doing some examples. And it's going to be fun. I'm looking forward. So here we go. I'm going to turn off my camera and let's get into the video. Honestly, I could turn it back on in a second if I so choose, like this. But anyway, bye. Great. Okay, let me just get the chat up. Okay, let's get started. So, we have a law. It was given to us by Newton, our God. And he basically said that we could define force, F, to equal ma, such that the amount of acceleration a object experiences will be equal to the mass of the object divided by, the force on that object divided by the mass of that object. And mass is like an inherent property of said object. It's like an inherent property of nature. Philosophically, none of this stuff makes sense, but intuitively it makes sense. If you push a very heavy thing, it will move less than if you push a very light thing. And that has to do with because the mass is being divided, and so the acceleration is less, because the forces and all that jazz. So, but the truth is, we don't have to think about it like that. Instead of saying F equals ma, we could say that F equals the mass times the derivative of velocity over, like, with respect to time, right? The derivative of the velocity with respect to time. This is true because the derivative of velocity is acceleration, and so basically we have the same situation. But really, even further, even like more so than that, and this is like the key. This is the most abstract we'll get, is that force equals the derivative with respect to time of mv, right? This is our big brother, our big lord, right? So normally we think that mass doesn't change over time, but what if your mass does change over time? So that's what we're dealing with. We're talking about the derivative of mv with respect to t, and this, just because of calculus, you understand that this equals, so F is going to equal the derivative of mass with respect to time times whatever velocity, plus the derivative of the velocity, which is the acceleration with respect to time, times the mass, right? And so this is what we had in the beginning when dm over dt is 0, right? When dm over dt is 0. So here, let's do it like this. When dm over dt equals 0, then the force equals dv over dt times the mass, which equals ma, which is the thing that we're used to. But what if, say, for example, the velocity is continuous over time? What if the velocity is continuous over time and the mass changes, right? So that would, to understand that abstractly, is basically saying we're at, like, either we're adding or taking away mass, and there's a force on the object such that while we add or take away mass, remember this is 0 because dv over dt is 0, while we add or take away mass, the velocity has to stay the same. And so clearly there's a force going on, and force equals dm over dt times v, which is all very, very interesting stuff. Great, so that's our basic understanding of force, understood from a lens of velocity. And this is important because we will define momentum. Let's see, yeah, where should I put this? Let's go over here. Let's just go over here. We'll define momentum as this, such that P is our momentum, and it will be a vector. P equals mv, okay? That's momentum. It's an attribute of an object. It's the momentum of an object is the mass of the object times the velocity of said object. With that understanding, you could say that F equals the derivative of momentum. Let's make all these vectors, right? The derivative of momentum with respect to time, right? That's interesting. That's just another way of writing the derivative of mv, which we wrote before. This is all very much the same stuff, right? So that's all well and good when we're talking about one object, but what if we're talking about multiple objects? Say we're talking about like a dust cloud of a lot of different objects, and they're all doing something together. So like we have this dust cloud of objects or something, and each one of these is a particle, right, with some momentum. And each one of them has some momentum, and they're all flying around. Great. So we could say that the change in the total momentum, how would you describe total momentum of these particles? The total momentum, the change in the total momentum of the particles, the sum of all the momentums of the particles. So let's put this like this: the sum of all the momentums. The change in the sum of all the momentums times with respect to time is what I meant to say, is equal to the force on all of those objects, but it has to be external. And it's the sum of all the external forces. Let's actually make this a subscript. It's the sum of all the external forces. Now, why is it external forces? Again, I'm going through this very quickly because we covered this a few lectures ago, but why is it external forces? Well, external forces mean forces outside of the system we're looking at. So say we're looking at this system, right? We're looking at this system over here. An external force might be a planet. Like, let's just say this is some big planet. It's an ellipse for some reason, and the planet is acting gravitationally. It has a gravitational force on all of these particles, right? That would be an example of an external force. An internal force is, say, for example, each of these particles act on each other with a gravitational force, right? They're all attracting each other. The reason why this won't lead to any change in momentum is because of Newton's third law, which is that every action has an equal and opposite reaction. So within this system, all of the forces that are acting on these particles from the system that we're looking at, they'll all just, the sum of all the forces will be zero. And so the change in momentum from internal forces will be zero. Whereas if we consider this to not be a part of our system, then it will be changing the momentum of our system of particles that we're looking at. And this is not too complicated, but it's a little confusing the first time you hear it. So it's okay if you don't fully understand it the first time. But anyway, that is our situation. Pretty cool. So now we have this understanding that the sum of all the sum of all the forces, of all the external forces, equals the change in momentum. The sum of the change in momentum. Okay, one more basic idea that I want to cover is called impulse. Let's cover it over here in this little area. I just want to make sure that everything is working, because sometimes, yeah, that's fine. Okay, impulse. Impulse is the change in momentum, but not divided by time. It's the change in momentum. So, for example, let's say momentum is a function of time. So we have p of t minus p of 0. Let's just say, like, t sub 1, let's say. And momentum is a function of time. And no, they'll be vectors. So p of t sub 1 minus p of t sub 0, that is the impulse that the object has experienced. Yeah, that's something that we call impulse. Another way of writing this is an integral. It's an integral from time equals from t equals 0 to t equals t sub 1 of the force on the object, f of t, times dt. Now, how does this make sense? Well, this comes from our understanding of integrals. So, for example, I'm not going to go through integrals right now and talk about how an integral, right, from this point to this point, let's say this is some function f of x, the integral of f of x from these 2 points is going to equal the area. It's a number. It's going to equal the area. It's not a function. Like this whole thing returns a number. So, but knowing our understanding of physics that we hopefully have from the past, we know that dv over dt equals acceleration, right? The derivative of velocity over the with respect to time is acceleration. And we know that the integral, we know that the area under the graph of acceleration, let's say acceleration looks like this, or actually, no, let's honestly just say that acceleration looks like this. The area under the graph from for two different points, right? This is the change in velocity. So dv equals an integral from some point, let's say t sub 0 to t sub 1, and let's say t equals t sub 1 and t equals t sub 0. That equal a of t dt, right? So we have this relationship that derivatives and what they're equal to is integrals from different points, and it's the change in velocity, right? Another way of understanding this, if we want to stay in calculus, is dv equals a times dt, right? If we just move the dt to the other side, and this is understood that if you want this to not be an infinitesimally small amount of v, if you want it to be a real delta v, that's equal to the integral, right, of a of t times dt. So with that relationship understood, this is just the change in the potential, right? I'm sorry, the change in the momentum. So with that understood, we can write that dp is, well, what was momentum's version of a, right? Like velocity had a, so momentum had f, right? F was the thing. We had dp over dt equal to f. So that means that the change in momentum is the integral from 0 to whatever time t you want of f of t dt. And I know I'm not writing this with proper syntax, but that's just the basic idea. So great, so that's a basic overview of momentum. Super cool, right? Let's just move all this stuff up a little bit. Awesome. All right, that's all the basic abstract stuff that I wanted to talk about. Now we can start discussing some fun stuff. Let's get to discussing some problems, shall we? Okay. I'm debating whether or not I should do colors, because the problem is if I do colors, I'm going to have to stay with the colors, and it's going to be a mess. I'll try one problem with colors right now. Okay. Say we have a rocket ship. And I'm going to make the rocket ship in red. So we have our rocket ship. This is a rocket ship. Okay? Good enough. Good enough. Awesome. And the rocket ship has some mass m. I'm not sure if I want the mass of the rocket ship to be lowercase m. Hold on. Let me think about this. How we're going to label this. Yeah, the rocket ship has some mass, big M. Yeah, big M. And actually, sure. The rocket ship has some mass. We're not going to write it down just yet. Let's just realize that the rocket ship has mass, right? And let's say the rocket ship is flying with a certain velocity v. Okay. Now the problem is there are dust particles, right? There are dust particles, and they're landing on the rocket ship as the rocket ship flies through space. Got a lot of small little dust particles. Some of them are a little bit bigger. I'm not sure if you guys could see. Let's zoom in a little bit. We have all these little dust particles, and they're landing on the rocket ship as the rocket ship flies through space. It's like space dust or something. I don't know. Whatever. The dust is landing on the hull of the rocket ship. So dust is landing. Dust lands at rate dm over dt. Very simple. That is the rate of the dust landing on the rocket ship, and it has a velocity with velocity equal to u. That's the velocity of the dust. Yes, yeah, the velocity of the dust with respect to the origin. So we have our origin over here. And we're just looking at things from respect to the origin, right? So the dust has a certain velocity u with respect to the origin, not with respect to the rocket ship, with respect to the origin. Okay, so the question is, given this system that we have over here, yeah, let's put it this way: how much force F is required to keep a rocket's velocity, rocket's velocity at v. Okay, that's our question. How much force F is required to keep the rocket's velocity at v? So you can understand that there are these particles landing on the rocket, they have mass, and so as they land on the rocket, things are going to slow down. And especially if u is less than 0, so if u is like a negative thing, imagine u faces this way, then not only is the rocket slowing down because there is more mass landing on it, but also it's being hit with things moving in the opposite direction, and so that itself is slowing it down too, right? In other words, it's being hit with all this little momentum, all these little momentums that are not the same as its momentum, and so that's changing its momentum. And we're basically asking how are we going to keep the rocket's velocity at v? That's the question. Well, let's think about it this way. Let's consider our system, our whole system, at time t. So at some time t. At time t. At a given time t, what do we want to be concerned with? Like, what are we looking at? Well, I want to know the mass of the rocket ship. So I want to know literally the mass of our rocket ship. I want to know this guy. I want to know the velocity of our rocket ship. And I want to know all the information about the dust that is right about to land on the rocket ship. I don't really care about this stuff yet because it's not going to factor into the collision. I really want to focus on the stuff that's right about to land on the rocket ship. And I actually want to treat that as one system. So I want to look at like basically this. Some of the dust that's about to land on the rocket ship and the rocket ship itself. And I want to take a look at what their momentums are. What their momentums are at this moment. And the momentum has to be the same, or rather the change, how would I say this? If there was no force on the rocket, the momentum would have to be the same after the collision. If the momentum is not going to be the same after the collision, the change in momentum is our force. The change in what would have been to what is going to be our force. So we're keeping the same velocity. That implies that a certain momentum is going to have to change because there's more mass. There's more mass moving at velocity v. And so that implies that the momentum of the system is changing, which implies that there's a force, and we can calculate that. So at time t, what is our momentum? So at time t, p of t. Now again, I don't mean the momentum of the rocket ship. I mean the momentum of the entire system that we're considering. These particles and the rocket ship. Okay? I want to know the momentum of all of them. And so we know that momentum, P equals mv, or it equals P equals the sum of all the mv's, right? So, well, what's our first mv? Well, our first mv is the mass of the rocket ship times its velocity, right? So let's write that. The first mv is going to be, let's say, big M. Now, the mass of the rocket ship, quote unquote, is changing over time. So at time 0, the mass of the rocket ship is just the mass of the rocket ship. But at time 10, for example, 10 seconds later, the mass of the rocket ship, quote unquote, is the mass of the rocket ship along with all the dust that has accumulated in those 10 seconds. So that's why M is a function of time. M is changing with time, if that makes sense. Big M is changing with time. So because of that, I'm going to put M of t, right? M is a function. M of, oh my god, for God's sake, just write it. Okay, M of t times V of t. Right? That's the rocket's velocity. Now, what's important to note is that in our situation, V of t is the same. It's never changing, which is important to note, right? We don't want V to change. Interesting. Okay, so that's the sum, that's the rocket's quote-unquote momentum. What about the particles? Plus, well, what's about to happen? Well, we're about to have some kind of change in mass, and the change in mass of our rocket is going to be the sum of all the little particles that are about to land. So to express those, I'm going to put dm, delta m, delta m, the change in the mass that we're about to have on our rocket ship, delta m, and this is the that's terrible. That's fine. No, that's still terrible. Sorry, I am not a professional teacher. That's fine. Okay. Mass that would land in next instant. And we obviously don't have a number for this. It's literally, or next time interval. Let's put it that way. Next, because instant would be like dm. Next time interval. Right? That's the mass that's about to land on the thing times u, of course, right? That's the velocity of the particles, right? So this is our momentum at a given moment. At any given moment, this is our momentum, which is great. It's the mass of the rocket ship at that time times the velocity of the rocket ship plus the mass of what's about to land times the momentum of what's about to land. Great. So it's just the sum of all the momentums. And now what we could do is we understand, right? We know from before, where was it? I put it up here. That momentum, hold on, that force, force equals momentum, the derivative of momentum, right? Here we go. Force equals the derivative of momentum from our force definition, right? And our momentum definition. So that's really awesome. What we can do now is we can take the derivative of p of t. So the derivative of p with respect to time equals our force. And it's actually the force that we're looking for. So let's see how we could take this derivative. Okay? Well, let's put it this way. Let's first think of this as I think I skipped a beat. Before we get to this, before we get to derivatives, let's consider something else. The time interval, here we go. That's not how you spell interval. Interval. And I'm going to put in parentheses delta. Actually, I'll make this a different color. I'll make this blue. Delta t. Right? That's our next time interval. Sorry, I just have to make that perfect. Okay. So now let's consider something else. Right? Let's consider the momentum. And actually, I have to make sure that I'll have room for this. Let's consider the momentum at t, our time t, that we were considering over here, right? T plus delta t, right? What's our momentum after that time interval, after delta t has already passed? Well, this should be fairly obvious, right? It's our mass has changed, right? What's our new mass? What's our new mass like that we're considering? We're considering m of t plus delta m, right? Because delta m has now become a part of our rocket ship, and then everything else, right? Everything else has become, now everything is moving at a velocity v, right? That's our momentum at time t plus delta t. Okay, so now that we have this idea, we can find the change. We can find the change in momentum between these two moments. Okay? Let's do that. Let's find the change in momentum between these two moments. So delta p is going to equal, what's our change in momentum? What we have is we have an m of t times v. Yeah, that minus m of t and v. So those three things are going to cancel, right? I just have to keep my pen on the paper so that it doesn't move. But you understand how these three things are going to cancel, right? The velocity over here is going to be distributed here, and that's going to cancel with this when we do subtraction, right? Cool. Then we have v times delta m minus delta m times u. Right? And sorry, did I mess something up? Hold on. I don't think so. Yeah. Hold on, let me just look at my notes. Yeah, it's going to be, okay, very good. So it's going to be v times delta m minus delta m times u. Let's write that down. V delta m, oh shoot, no, I have to write this properly with the appropriate colors. V times delta m minus delta m times u. And that, for some reason my thing erases stuff even when I write it. I don't know why. That equals, stop erasing my stuff. That is simply going to equal delta m times v minus u. Right? So that's our change in momentum. Oh, excellent. Now, how about our change in momentum over time? How about delta p over delta t? You know what, I'm not gonna make delta t blue. Yeah, it's just delta p over delta t. That is gonna equal delta m over delta t times v minus u. Right? That's our change in momentum over time. That is really cool. Like, already, this is super cool. We know what our change in momentum over time is. It's the amount of mass that it's the change in mass of our rocket ship times the velocity of our rocket ship minus the velocity of our masses. That is super awesome. So if you told me what's the change in momentum over 1 second, I could tell you. But now we get something really interesting. Right now we're about to get something really cool. What are we going to do? Well, what happens if we take the limit as delta t approaches 0? In other words, as delta t approaches dt, right? What would happen then? Well, let's take a look. If force equals dp over dt, that, because of what a derivative is and because of what a limit is, that's going to equal our function here as delta t approaches 0, right? That's what a derivative is. It's, you have the upper function, you have the upper situation, you have basically the f of x. This is our f of t. This is our change in momentum, or this is our f of t really. And then f of x, yeah. So you have your f of x over x. You have your delta f of x really over your delta x. And what happens as delta x approaches 0? Well, then you have your derivative for that function. And if momentum is a function of time, then that's exactly what we want. So this could be expressed as the limit as delta t approaches 0 of, I'm just going to bring all this over. Copy. Paste. Super cool. Now this over here is a constant, right? So our limit doesn't care about that. So let's rewrite that with our limit not caring about that. Shall we? Yeah. Let's rewrite that with our limit not caring about that. That's going to be, I'm honestly just going to copy this whole thing, and I'm gonna paste it over here. I don't think I have room actually. That's a little bit unfortunate. I'll put it down here. I'll put it down here. Fine. Let's take out the v minus u. You know what? Screw this. I am just going to do it manually over here. We're not making anything new. So let's bring it over here. Let's bring this over here. Bring this over here. Right? You understand why this is happening. The constant doesn't care about the limit, right? I don't know why delta m has an underline, but you know, I'll just get rid of this, and there you go. So now what is delta m over delta t as delta t approaches 0? Well, the change in momentum is a function of time, right? Right? It's delta m of your delta t, right? Your change in mass is a function of time. How much mass you've changed by, how much mass the rocket has changed by, depends on how much time has passed, right? You see that the particles are landing on the rocket. And so as time gets infinitesimally small, the change in mass will be infinitesimally small. And so this is all going to equal, this tells me that dp over dt equals dm, sorry. Actually, no, I'm not going to, yeah, I made it orange above, so I'm going to make it orange over here. Equals dm over dt times v minus u. And there you go. That is your change in momentum. Now, why is this amazing? Well, because your change in momentum is your force. And so rewriting all of this, we know that our force, the amount of force that must be applied on the rocket every single second, every single moment of time, is dm. Sorry, I don't want color. It's weird. Copy. Is dm over dt times v minus u, which is absolutely beautiful. We solved that question. Isn't that amazing? I think that's amazing. Okay, great. That is the first question down. Isn't that fun? Let's move on to another question and another page as well. Super fun. I'm having a great time. I don't know about you guys. All right, new question. Oh, let me just check my notes to make sure that that was a correct answer. Yep, that was a correct answer. dm over dt times v minus u. All right. Now, how about let's think of another question. Imagine we have like a railroad. It's a railroad. Don't question it. I'm going to zoom in a little bit. I think my roommate's coming. I can hear him singing. I can hear someone singing, and I know that my roommate sings. All right. Imagine we have like a train. Here we go. Here's our train, and sand is being dumped into our train. Right? So sand is coming. Actually, no, it can't be like this. It can't be like this, because that would imply that the sand has some momentum. And all I want is for the sand to fall. Right? I don't want any momentum. So again, we have like these dust particles, and they're falling onto the train. Into like, I don't know, maybe like there's some basket on the train that's ready to receive them or something. Right? Okay. And also our train has to have wheels, of course. Great, here we go. Here's our train. Oh no, my wheel gone. My wheel disappeared. Great, so here's our train, and there's sand coming down and falling onto the train. And great. Okay, here's the deal. The train has some force. Let's say the force is pushing it. Right? Some force. And it also has some velocity. It also has some velocity. Okay. And actually, you know what? Velocity doesn't have to be a vector, because we are only considering one dimension of motion. Only along this horizontal situation. So, right? We're only considering one dimension of motion. Okay, now here is the thing. What are we trying to solve? I don't even remember. What am I trying to solve? Maybe we're trying to say, what is the force? Yeah. What is? Let's do the same problem. Same problem, but different situation. What is F such that V is constant? How do you spell constant? I'm just gonna say const. Const is good. Okay, and that's a question. All right, so what is F such that V is constant? Well, that's a wonderful question. Let's do a very similar situation. Let's do a very similar process of understanding things. So let's consider it at time t, right? Well, first of all, it's just force equals dp over dt. You find the dp over dt, you find the force. So that's what we're going to try to do. And the best way for us to do that is just to find the delta p over delta t, right? That is the basic understanding of how we're doing this. So let's do that. Let's consider two instants of time. We're going to have p of t, and we're going to have p of t plus delta t, right? What is p of t? Well, again, let's remember what we're considering. We're considering the train, and we're considering the few dust particles that are about to land on the train. And that is what we're considering as our p. Like, what is the momentum of that? That is our system. We are not considering anything else simply because they don't get involved in our time frame. Within delta t, these guys don't get involved. It's only these guys that get involved, and that's why we're looking at them. Okay? So what is the momentum? Well, the momentum is the mass of the train, m of t, right? M changes with respect to time, so m of t, times v, right? Because that's how fast the train is moving. And honestly, yeah, again, v does not have to be a vector. Plus, we have the mass of the particles that are about to land. So let's put that as in terms of delta m. Ooh, was I supposed to give information? Yeah, I was. The particles are falling at a rate of dm over dt. Like that is how fast that they're coming on. That's just the thing. You need to know the rate at which the particles are falling to do this. So anyway, and it's a constant rate as well in this case. Anyway, the momentum of the particles about to fall is dm times 0, right? Because they don't have any momentum in this or that direction. They're only falling down. So it's just times 0. Great. That is the momentum at one point in time. Now let's do the momentum at another point in time. The momentum at another point in time is the sum of the masses times whatever velocity we have, and the velocity has stayed constant. So it is velocity times m of t plus delta m. Great. Those are our two things. Now let's find the difference in the momentum, right? So this tells me that dp equals, again, these two are going to cancel. These two are going to cancel. Sorry, I should really do this with the laser so I don't have to delete stuff and also so that it's less confusing. These two are going to cancel. And so all we will have is, we will have delta m minus v, right? Delta m minus v. Actually, it's going to be delta m times v. Sorry, delta m times v minus, well, that's all there is. Like, there's nothing there. So it's just delta m minus v. So the change in momentum is v times delta m. Right? That makes sense. These two will cancel. And that's all that there is in this term. Like, this is 0, right? So the delta m and the v don't have anything to cancel with, and so it's just v times delta m. I was confused for a second because I thought it was going to be a negative, but then I realized that it wasn't, and so we're good. Great. Now let's recognize that. How much room do I have? Oh, okay, hold on. Not that much room. So now let's recognize that delta p over delta t equals, and you probably have seen this before, delta m times v divided by delta t. Great. We are basically done, right? If f equals dp over dt, and dp over dt equals the limit as delta t approaches 0 of delta m v delta t over delta t, and that equals, because of how limits work and because of derivatives and whatnot, that equals delta, I'm sorry, no more deltas, it's just dm over dt times v. That equals our force. And this makes sense when you remember something that I told you before. I already told you this, right? Force, where do I have it? Force equals delta m times over delta t v plus delta v over delta t m. If delta v over delta t is 0, then force equals dm over dtv. And that's exactly what we have. We have dm over dtv because v is constant, and that's all that we have, because dv over dt is 0. Excellent. That was a much simpler problem. I hope you found that one quite simple. moving on. One more problem for us to enjoy. Like I said, I hope you guys are having fun. I'm having a blast. Let's see, are there any comments? No, no one is here. Okay, that's fine. I'm okay with that. All right. The next one we have is going to be a rocket that is losing fuel. And there are no external forces on the rocket. And let's just describe what's going on. Right? So let's draw this. Let's draw this out. Here we have our rocket. It's flying to space. Sure, that's a rocket. I don't know. It looks a bit like a sword. Like if we had a pommel here, looks kind of like a sword. But it's a rocket. It's a rocket. Here, I'll add a little cockpit. That probably made it worse. Here, let's do that a little bit better. Here, I'll add a window. Bunch of windows. This is just terrible. What a disaster. Okay, there you go. Here's our rocket, and it's got like some fire. There you go. There's our rocket. And let's move this over to the side. Okay, and the rocket has some amount of fuel in its tank, right? You know what? I'm gonna get rid of some of the windows, and we're gonna make a separate compartment, right? Here is where all the fuel is, right? And the fuel is being used up by the rocket, and and that's what's causing it to fly. That's how rockets work. Sure. Okay. The question is, at time t, rocket plus fuel is moving, hold on. I'm not sure what this is trying to find. I'm not sure what this question is. I'm looking at the question in my notes, and I'm not really sure what we're trying to solve. Let's actually, you know what, let's just find our change in momentum, our delta p over delta t. All right, let's just see if we could figure this out. What is dp over dt? Well, let's set a few things. Let's understand a few things. Oh, I'm looking at my notes now. This is weird. Okay, let's understand a few things. The fuel, I don't know why I can't write. Fuel is going out with velocity u, and yeah, I'm gonna have to make that a vector, aren't I? With velocity u, with respect to rocket. Okay, so first of all, this means a few things. A, the rocket's not burning the fuel. Rather, apparently, the fuel is like being thrown out of the rocket. Okay? And that's what's giving it its thrust. Sure, why not? And from the rocket's point of view, like basically from the pilot's point of view, I was about to draw the pilot, but from the pilot's point of view, the fuel is flying out with a certain velocity, the velocity of u. Now, it's important to know that that's not the fuel's quote-unquote actual velocity. We're going to have to find a non-accelerating reference frame. Okay? Okay. Let the final velocity of the rocket be v plus delta v. Here, yeah, okay, let's also understand another thing. Let's move this down. One thing that's more important than this is that at time t, the rocket plus the fuel, and when I say plus the fuel, I mean plus the tiny bit of fuel that's about to leave the rocket within the next time frame, within the next delta t. Rocket plus fuel is moving at here velocity v, or maybe the rocket plus the fuel. Yeah, the rocket plus the fuel inside the rocket, I guess, is what I meant. The rocket plus the fuel is moving at with the velocity v, such that if we understand the momentum equals the mass of the rocket plus the change in mass, the fuel that's this is the mass of the rocket plus most of the fuel, and this is simply the mass of the fuel that's about to leave the rocket. So mass of the rocket plus delta m times our velocity, times the velocity of the rocket. And I guess is it v of t? Is our velocity constant? I'm not sure. We'll figure it out. We'll figure out what this means. Yeah, I'm not sure if the velocity of the rocket is constant or if it's changing. I imagine that it's changing. I don't think that we would do another constant velocity problem. But anyway, the point is we have a velocity. And that's an objective velocity compared to whatever reference frame we're going to set up shortly. Okay, so the rocket is accelerating at time t plus delta t. Velocity of that's a vet. Why not vel rocket? Sure. Equals. This is very silly, but v plus delta v. The velocity. I'll make delta v black. So whatever the velocity was before plus delta v. Right. These are vectors. Okay. And then now we have to think about what is the velocity of the fuel, right? What is the velocity of the fuel? So we can't use the rocket because the rocket is accelerating. We can't look at u as our thing. What we could do is we could look at this. We can construct our reference frame. There's something sticking on my tablet. Ew. Hold on, let me rub this off. Ew. What is this? Sorry, you see drawing, but I'm actually just rubbing my tablet to clean it. And the drawing went away for some reason. Anyway, I didn't erase that. It just went away. Okay. So let's construct our reference frame. This is our reference frame, these coordinates. And how are we going to understand velocity u? It's a wonderful question. So in terms of this situation, well, let's understand that Let me think how are we going to do this. Well, let's put it this way. The rocket has some position. It has some position. Hold on. It has some position r. That's its position. Oh my god. And the fuel also has some position. Let's just pretend that this is the position of the fuel that just left. Every individual particle of fuel also has a position. Let's call this r over here. Oh my god. Now, the thing comparing the two, the position of the particle, the position of the fuel relative to the rocket, is this thing. Oh my god, let's make this a different color for God's sake. Let's make it. Well, honestly, you know what? Hold on. I'm gonna switch our situation. This thing we should denote as being, yeah, the position relative to the rocket should be r, as the orange. I know it's a little bit hard to see, but that's its position relative to the rocket. And then we have its like actual position relative to our reference frame is, let's say, this will be r prime. I don't know. Why not? R prime. I don't know if that's how you say prime. It's just, okay. So great. So now we have this idea that r prime, I think that's how you say prime. I'm not sure. Or right prime. I'm not actually saying anything. Equals r, the position of r, plus our relative position vector, which we don't actually like. We don't actually like relative positions, right? Okay. So now, if we want to get the speed, if we want to get the velocity, we could say that that v prime is equal to, yeah, it's equal to dr over dt plus d little r over dt. And this tells us that the velocity of our particle equals, well, what is the velocity of our ship, really? That's what we're looking at when we look at d big R. Well, the velocity of the rocket was v plus delta v. And so v is constant, right? Basically, between each, v is not constant, but between comparing two moments in time, we could treat v as constant, and delta v is how much v will change by. And so vf, right, like true v is going to be the sum of those two things. But for now, we could just treat v as constant, so the derivative of that is just v. Let's put that down. This is going to be v. And then delta v is confusing. Yeah, it's a good question. The derivative of delta v with respect to t is going to be, yeah, dv over dt. But for now, let's just think about it as, hold on, this is a little bit problematic. Oh, what am I doing? I'm not taking the derivative of the velocity. I'm just taking the velocity. I'm an idiot. Yeah. So dr over dt is the velocity of our ship, and the velocity of our ship after delta t, like after some time has passed, which is what we're looking at. We want to find we really want to find a u in terms of the velocity of the rocket. We want to find u. And u is after the particle has left the rocket. And so we'll be concerned with the velocity of the rocket after the particle has left the rocket, and the velocity of the rocket after the particle has left the rocket is v plus delta v. Let's just put that down. V plus delta v. And then last but not least, we have dr over dt, which is just u. Let's put that down. Plus u. Beautiful. And so this is our velocity of our particle with respect to the actual reference frame, which is what we want, right? So when was my midterm? Oh, my midterm was last Tuesday. Oh, it's Tuesday right now. That's crazy. Okay, I was just thinking because we don't have homework, and so I was confused. But anyway, yeah. So velocity of fuel. I'm gonna put like true velocity of fuel, or something like that. True velocity of fuel. Great. Okay, now we have a bunch of things. We don't really need the u anymore because we found a better thing, but we do need the u because we need the u for this. And we know the velocity of the rocket after the fuel has left. We know the velocity. We know the momentum. Yeah, we know the velocity before the thing left. We know the momentum before the fuel left, which is all good. Okay, so now let's understand things a little bit more. Let's get to solving this issue. So we have p of t plus delta t. Let's take a look at what is the momentum of our system. And again, the system that we're looking at is the rocket plus the little bit of fuel that just left. We have to keep both of those into account. Why? Because before this was also looking at. We're looking at the momentum. I'm going to put this like p of t. Right? This is the momentum of the rocket plus the little amount of fuel that was just about to leave. And so we have to think about the same momentum function, taking the looking at the same objects, but now they have different velocities, so that we could find out what the change in momentum really was. And so the momentum is going to be the mass of our rocket, like the mass of the rocket without the little fuel that just left, so that's going to be m, times the velocity of the rocket, but after this whole process, which is going to be m times v plus, and I'm gonna make delta V black, because I think delta V is something more important, because delta V shows up over here too. Not more important, but more universal almost, as opposed to V, which is the velocity of our rocket. So it's going to be that's the velocity of the rocket part. Now we need the velocity of the particle part, which is going to be plus delta m times the velocity of the particle, which again we understood to be v plus delta v plus u. And u is a given, so it's okay to have it, like we were given u. Great. Here is our momentum afterwards. I'm going to have to make this a vector. And this one also should be a vector. Great. Okay, now let's do the same thing. The delta p. So that's, oh my God, for God's sake, just write it. Let's actually write this one down. We haven't written them down before. Let's write this one down, just because there's so much doing. So it's going to be m times v plus m times delta v plus delta m times v. Sorry, that should be red. Plus delta m times delta v. Ooh, that's interesting. Maybe you're already seeing what's going to happen to delta m, delta v. I don't know. I think I have an idea. I could be wrong, though. Oh my God, I keep on forgetting to switch colors. Right? Plus delta m, delta u. This is not making this any easier to understand. Delta mu. Okay, that's our first thing. Okay, all of that minus, right? It's gonna be minus, and let's just bring out the p of t, which is gonna be v of m plus delta m of v. So minus, not v of m, but rather v times m plus, it was v times delta m, right? Yeah, v times delta m. V times delta m. Okay, quite clearly, these two guys are going to cancel. These two guys are going to cancel. And so we're going to be left with the idea that delta p is a much longer one, isn't it? Equals, delta p equals m delta v. M delta v plus delta m delta v. Plus delta m delta v. Okay. Plus delta m. Yeah, delta mu. Okay. Awesome. Okay, we can, I think we could do some factor. Let's do a little bit of factoring. Or maybe not. I don't know. Hold on. Now let's set this, right, so, okay, here was our change in moment. Okay, I guess we are solving for, what are we solving for? Solving for force? Like, what is the force that's launching the rocket up? I guess we're just solving for delta p or something. I don't know, let's just solve for dp over dt. Okay, so to solve for dp over dt, given this situation, let's just set everything divided by t. So dp over dt. Oh, that's interesting. Hold on. Nope, no, that makes sense. Sorry, my bad. dp over dt equals, and now let's just copy this whole thing and paste it. Great, and then of course that's just going to be set over delta t. Okay, now let's take the limit of that as it approaches 0. So the limit as that approaches 0, I'll write it out. The lim as delta t
approaches 0. That equals the limit of delta as delta t approaches 0 of this whole mess. Paste. What does that equal? That's a good question. Let's figure it out. We could just understand limits, and let's evaluate each of these individually. So we're going to evaluate this one, and this one, and then this one, and then we'll do this one. So let's do that. So the first one, how much room do I have? Not that room on the bottom, but I have all that room on the side. Okay, let's go to the side now. Okay, so the first one is going to be, m is not affected, so it's just going to be m dv over dt. dv over dt, right? Plus dm over dt. Ooh, actually, that's interesting. That's very interesting. Yeah, I thought about this. I thought dm times dv, or delta m times delta v. I think that's just going to be 0, right? As delta t approaches 0, I think this thing approaches 0 as well. Yeah, I think so. I think that's how that works. Yeah, it's going to be like, it'll look funny because we never see this, but it's like dm dv over dt, and this quantity like is tiny. It's like negligible. So we don't even have to think about that. Like that just approaches 0. This whole thing approaches 0. So this approaches 0. And so then all we have left is dm over dt times u, I believe. And that is this equals dp over dt. And I believe that if you want to understand this, this is the force that the rocket experiences from launching out all the fuel. Like that's like that there's an equal and opposite force, we could and it's going like this. And it equals, right? So there's a force kicking all the fuel out, and there's a force kicking the rocket forward, and that force equals this thing. It's the change in momentum, right? So I believe that's the deal. I believe that's the more abstract understanding of what's going on here. But I could be wrong. Anyway, that last problem was a little bit iffy. I have a physics lecture in an hour, so I'm gonna leave that there. I hope you guys enjoyed. We covered a lot of cool stuff. 2 awesome, very colorful pages of physics. I think that this was pretty fun. Yeah, anyway, I'll see you guys in the next one. I'm going to end the stream now. So, yeah. I suppose that's it. Hold on. It looks as though Anyway, I'm going to end the stream now. So, it's just things seem a little bit delayed in the stream. So, I'm going to give it a minute just to make sure that all the content is there. But anyway, I'm ending the stream. Check out the previous videos in the description below. I believe they're in the description. If not, you can find them on my channel. Maybe consider subscribing if you enjoyed. I don't know. Hope you have a great day. I will see you guys in the next one.